So, one of the good data sets is illustrated here. So, when we do the data collection and collect the data over the on a crystal, it is not just a few 3-4 hours data set. The data that is collected is now has to be complete, and we have to see whether we have got the data on every reciprocal lattice point which comes in the limiting sphere, and in fact beyond the limiting sphere in some sense. We also measure all possible reflections. We do not leave out the reflections now, and as you see from this, this is the structure of epsilon which was done in our laboratory. Epsilon polymorph 2, it is supposed to be a drug, and the temperature at which the data was collected is 100. This was done by my student who is now his name is Dr. Sajesh Thomas, and he is now somewhere in Denmark. So he measured the data at 100 Kelvin, and the wavelength that is used is molybdenum. And as we saw from the table we made for resolution limits and so on, lambda by 2 is the resolution to which we can go in principle, right. So it should be half of 0.7. So we should be able to see these bonding densities fairly clearly in this data. Sin theta by lambda, he managed to go up to 1.08. And the total number of reflections collected, as you see, is enormously large for a very small crystal unit cell dimensions. I think the unit cell dimensions are not given here, but I remember the unit cell dimensions. It's a monoclinic system, and it is 8 by 12 by 14. It's a very small cell. So you see that we have 1,12,503, out of which, of course, all the redundant ones are also measured. That means we measure the Friedel equivalent also. So the Friedel equivalents do not contribute freshly to the data, but they will allow you to average the data. So if we now reduce this redundant data to unique reflections, we have 11,087 reflections. So in fact, if you look at the sphere, Ewald sphere, you see that it is 100% complete data. That's all possible data points have been taken into account. A very high quality data, and we have measured some reflections more than 10 times. That means if we have measured, let us say in this space group, we have measured 10%, 10.2 times is the redundancy. That means a given HKL is measured in all possible orientations 10 times. So and then averaged out. So your accuracy of the data measurement is extraordinarily high, and that is indicated by this what is known as a fractal plot. So I have no time to go into the detail, except that this has to be symmetric with respect to the electron density, the residual electron density, which is shown here. So based on this, now we go to the refinement. So we now refine the unit cell in such a way that we consider this as routine data. That means we do a spherical atom refinement. So when we do this spherical atom refinement, we reach an R factor which is 0.02, very accurate data, and the weighted R factor is 0.08, and the goodness of fit, which should be ideally 1, is 1.038. That means it's an extraordinarily high quality data. And as you can see from here, if you do look at what is left after the difference Fourier map, you see that the amount of electron density that is left is minus 0.79 electrons per angstrom cubed to plus 0.79. Both are nearly equal. That means it is a very flat map after you account for the entire data, entire crystal and the atoms in the crystal. Then we go and do this multipole refinement. You see the number of reflections now used are 8,038. We have made some more filtration of that, because we now consider reflections above the threshold of 2 sigma I. Sigma represents the threshold. So the ratio, see what is important in this data again is the over-determinacy. Just like any structural refinement, we had over-determinacy. Here for every variable which is now increased in number, because now the variables are not just x, y, z, we have to now refine many other parameters to define this asphericity. In fact, every atom earlier had x, y, z and 6 thermal parameters, so that made it 9 parameters per atom. Now along with this 9 parameters, we now consider the atom to be a multipole. That means the atom is now associated with a monopole which contains the number of electrons. Then it is also associated with a dipole, so which will have 3 parameters, 1 parameter for the monopole, 3 parameters for the dipole, and then 8 parameters for the octopole and so on. So, we will keep increasing the number as we go higher and higher to describe the atom. So, effectively what we do is the following. You just consider the atom to be made up of a monopole, and this particular monopole now covers the diameter of the atom, and then in that we have a dipolar contribution which will go like that with respect to the center and 3 directions, then the quadrupole, the octopole and the hexadecapole. So, effectively we fill in all the possible space here, and the shape being aspherical, the space being aspherical, we will have the representation of the atom in terms of multipoles. That is why we call them multipoles. So, there will be 26 additional 9 plus additional parameters are counting to total 26. So, we therefore refine 26 parameters per atom. So, considering that, the number of reflections to number of variables ratio is 19. So, it is generally recommended it should be at least 10 for a successful determination of bonding density. So, it is quite over determined in that sense. So, the R factor here you see is 0.016. That means the error that is involved is less than 1.6%. You can express the R factor as 1.6%. That means the 1.6% is your R factor, the weighted R factor is 3.7%, goodness of fit is 0.87. In fact, if once we compare this to f ops minus f calc, you see this line where in which we have plotted every reflection that has been measured, and you see they follow a beautiful straight line saying that there are not much deviations in the individual f ops f calc measurements and calculations. So, this essentially represents a very accurate data. It is P21 upon C, as I mentioned, it is a monoclinic system. What are the experimental requirements? How do we collect the data in such an experiment? The experimental requirements are we can use a conventional source, a good laboratory source, and the preferred radiation is molybdenum. Of course, we can also use silver, because the idea is to get the sin theta by lambda maximum to as high a value as possible. Obviously, use of copper is disallowed because it is just up to 0.65. We need to have data beyond 1.0 of sin theta by lambda, and so molybdenum is the choice if you are doing charge density analysis. We can use synchrotron radiation and tune the radiation in any range between silver and molybdenum, so that is also good news. We can use rotating anodes as well. The detectors could be CCD image plate. I must be adding here a CMOS detector, which is nowadays the most suggested detector on diffractometers. The low temperature data, we can use either nitrogen or helium. We use nitrogen, which is about 100 K, because in all these there is one issue, there are 2 issues in fact. The 2 issues are the 2 which are ticked. Only when we can tick these 2, we can do the charge density analysis, and therefore aid in the development of the ideas of quantum crystallography. So, we have to have good quality crystals, that is the first requirement. The second requirement is that we should have a good electron density model. So, once we have these 2, this is the multipole model which we just now discussed. If we have these 2 properly done, then we can go further, and now we can bring in the aspect of combining theory and experiment. One of the early ways of doing this was, sorry about this overlap, it is University of Torino, this reference is 2006, but we have now what is known as Crystal 17. I told my students to get it, but they have not shown any further interest on that. We have Crystal 17, and the Crystal 17 is the one which we should be having, and the theoretical calculations can be performed, and we can use the package XD, which is the charge density package. So, when we take the charge density package and use this program Crystal from the charge density package, we feed in the coordinates, the lattice parameters and the basis set. Then periodicity and symmetry are brought into this system. We can use Hartree-Fock and DFT etc. to calculate the wave functions and reflections. See, the advantage here is we end up with theoretical structure factors. So, if we get theoretical structure factors, they are devoid of all systematic errors. We do not have to worry about absorption, we do not have to worry about extinction corrections, we do not have any issues related to WLP and so on. All whatever errors we have had in the routine structure determination are avoided. So, the theoretical structure factors are the ones which we now use, and of course, we use the XD protocol refinement, that is the charge density refinement, and process the data. There are two ways in which we can do it. One is, of course, we have the wave functions. This is the quantum crystallographic approach. So, we have the wave functions, we can go back here, recalculate these values and then feed into crystal and then develop the theoretical structure factor. So, or we have the reflections, these theoretical structure factors are essentially the reflections. We can therefore cycle these out such that we get finally a high quality theoretical structure factors which can be taken to refinement. So, this is the approach which is there in crystal package, and now we have to see how to see these atoms. You see, we have done the map, the multipole modeling, we have accounted for the overall electron density and so on, but how do we see these atoms? There is a theory due to Bader which is referred to as atoms in molecules. There is a book which is Atoms in Molecules, a Quantum Theory, published by Oxford University Press in 1990. This was written by Richard Bader. So, in this approach what we do is we do not look at, you see, nobody told us that when we say a bond between an atom, let us say one carbon and another carbon, nobody told us that there should be a straight line between these two, which we call as the bond length, but there is nothing called a bond length. Okay. There is electron density between the two atoms and it is shared, and the electrons do not know that they should go in a straight line. Nobody told that you go in a straight line, but we measure the straight line distance and say it is bond length. And then the same thing is true with the bond angles. Then we take the two lengths and then say this is the bond angle. What really happens is that the electron density gets distributed in this region. So, it is now a three-dimensional issue of the electron density distribution, and therefore, we call it as the topology associated with the bond. So, effectively you see here, if you take this as a carbon atom and the other end as a carbon atom, this is the CC bond. The electron density is distributed inside this cylinder. It is not necessary that it should be a straight line, it can be anywhere in this particular cylindrical entity, which is characterized by three quantities, lambda 1, lambda 2, lambda 3, which are essentially elements of what we call as a Hessian matrix. Theoretically what it means is that we have the true chemistry of this bonding is represented in terms of an expression which is the second derivative of the electron density at the so called critical point. The critical point is one in which the first derivative of the electron density goes to 0. So, between these two atoms, the first derivative of the electron density goes to 0 at a critical point. And whenever there is a critical point between two atoms, in principle we call it a bond. And if there is a bond at the critical point, del square rho value should be lambda 1 plus lambda 2 plus lambda 3. And there are different kinds of bonding features, and those are indicated here. I do not have time to explain every one of them, except to tell you that these are actually tensors of rank 3. So, if it is 3 minus 3, it represents an atom position, 3 minus 1 represents a bond position, and then 3 plus 1 represents a ring, and 3 plus 3 represents a cage. Effectively, we are now trying to see what is the chemistry in this bonding, rather than look at the straight line distance between atoms and so on, which is important, which is important to say, find out how accurately we can determine those straight line distances. But what is important is now to see the electron density and how the electron density is distributed between these two bonds. So, whenever this value of del square rho c, which is called the Laplacian, is less than 0, it represents that the two atoms here involved are sharing the electrons. It is a covalent bond. What is defined as a covalent bond by Linus Pauling is exactly the fact that the del square rho c is less than 0. If del square rho c is greater than 0, it represents closed shell interactions. That means if you have, let us say, a molecule here and a molecule there, and these two molecules are interacting through a hydrogen bond or some other van der Waal interaction, this essentially represents the limit of the van der Waal interaction. That means there is no density developed at the critical point. It is now del square rho c greater than 0. In both the cases, there is no density of the first derivative of the electron density, that goes to 0. We also now define, because we know these values lambda 1, lambda 2, lambda 3, these are the eigenvalues of the Hessian matrix, as I mentioned. These are all terms which I am using freely. These things need a full another 30-hour NPTEL course in which we can kind of systematically go and define all these factors. But what is important from the chemistry and what is important from this particular course structure point of view, structure and symmetry in the solid state, we are now trying to see the structure in the bonding regions and the structure in the regions between molecules and see if symmetry is still there and how the symmetry is directing the electron density distributions. So from that point of view, we are discussing this issue of quantum crystallography. So if we define a value epsilon, which is referred to as the bond ellipticity, as I mentioned again, that as we mentioned again and again, it is not the central straight line distance between the two carbon atoms. So this bond ellipticity tells us the nature of the bond. So if the epsilon is exactly equal to 0, it represents a sigma bond. If epsilon is greater than 0, it represents the nature of a pi bond. The fact that we can use multiple atom modeling and use the multiple atom modeling to look into the topological distribution is a very nice idea, because we now know whether the given chemistry can be represented for a molecule and so on. We will take examples. But before we go for such examples, I just wanted to introduce the other aspect which is now becoming very popular. This is known as the Hirschfeld atom refinement. In this particular case, what is done is to determine the structural parameters from single crystal diffraction data with very accurate possibilities, of course, independent atom model. So the structural parameters are from the independent atom model. And then we use the aspherical atom partitioning of tailor-made ab initio quantum mechanical molecular electron density. A big word, big phrase. So let me tell you what it does. What it does is, now that we have a molecule and let us say we are looking at the intermolecular space. So there is a molecule A and a molecule B, and we want to see what is the type of interaction this molecule A can have with the molecule B. So there are different kinds of atoms. There are atoms which are electronegative, atoms which are electropositive, atoms which are neutral and so on in this molecule, and so also in the other molecule. So if you now consider even the case where we have only two atoms and for a diatomic structure, let us say, and this diatomic structure, the interaction between two atoms, so effectively we replace the molecules by single atoms. The atoms between these two, the distance between these two, of course, is our bond length, but the fact that there is a certain amount of overlap of the electron density from atom 1 to atom 2 and a certain amount of overlap from 2 to 1 in the topological region defined. When we use the multiple atom modeling, the problem is that the multiple atom modeling does not restrain the extent to which electron density can be penetrated between the two atoms positions. So that means there must be some position. So the position is defined by what is known as atomic basin, in which we have, let us say, an atom. In this case we can use this diagram. So we can have an atom here and an atom there, and del square rho, the first derivative of electron density, goes to 0. So if you now plot the electron density along this particular direction, the first derivative of the electron density, when it goes to 0, that represents a maxima. So the actual amount of electron density that is at the middle of the bond is maximum, and then it falls off towards the other atom, it falls off towards the other atom. On the other hand, when we do the multiple atom modeling, the multiple atom model will have the populations of the higher terms, higher multiples, which are extended beyond this region where there is an atomic basin. So we have an atom, and between the two atoms, let me write it quickly because of lack of time. So we have an atom here, and an atom there. So, the electron density will go like that. So, this is the so called critical point. So, the first derivative goes to 0, and this essentially means that these two atoms are held with respect to the electron density region in this topological space. So, the expressions which we have for the multipole refinement modeling will extend beyond this particular point, which is strictly not allowed, because this is the place at which these two should be separated from each other. So, whatever contributions that are coming from multipole modeling has a tendency to penetrate beyond this, and therefore, there is error. There is an error that is associated with multipole modeling. This gets avoided when we do a different kind of modeling, and that again has been developed by using mechanical molecular electron density. So, if you now consider the molecule as a whole and calculate its electron density, there is a certain form factor which can be straight away attached to the molecule as though it is some kind of a thermal parameter. And so, we have a thermal parameter surface 1, thermal parameter surface 2, which now interact with each other. So, the atomic basin now can be better defined. Between the two methodologies, there is not much of a difference, except that we have, therefore, I have written here the difference between multipole expansion and Hirschfeld surface is in the partitioning of space between atoms. And this in fact allows for the computation of hydrogen atom position. So, we can actually compute where the hydrogen atoms are lying, and also we can get their corresponding atomic displacement parameters. So, this is a limitation in the X-ray experiment. We said that we cannot determine the hydrogen positions, but we use this approach and use either the multipole modeling or this one, preferably the Hirschfeld surface modeling. Then we will get the hydrogen atom positions. So, in some sense, this methodology of Hirschfeld atom refinement is similar to that of neutron diffraction. I think I should not go into further detail of this, or for that matter multipole model. Instead, what I will do is I will start taking examples which will make your life comfortable, because you will understand it better. And of course, you all know the story of Gulliver.